Rakesh, take over maybe.
Hello. Yes, good afternoon. Welcome everyone. Today we have Mihir Sheth from IISc Bangalore. He will continue part two of his talk that he gave last week on representations of p-adic groups.
Yeah, thanks.
Mihir, please.
Okay. Yes, thanks, Rakesh, and thanks again for the invitation to give lectures in this program. So I will continue with the second talk on representations of p-adic groups. Okay. So today we will be sort of talking about various types of representations, mainly the parabolically induced representations and something called supercuspidal representations. So let's begin. So G is going to be a p-adic group, and H will denote a closed subgroup. So recall that p-adic groups are locally profinite topological groups. So a closed subgroup is also going to be a locally profinite group. And in the last lecture, I introduced the category of smooth representations of locally profinite groups. So we start with a smooth representation of this subgroup H, and then we are going to see two ways of producing representation of the ambient group. Yeah. So like as usual, these are induced representations. So the first thing is something called smooth induction or smooth induced representation of G. Whose underlying vector space is the space of all functions from G to W, where W is the representation space for sigma, a smooth representation of H. So the function satisfying this usual property of the induction, and furthermore we need this condition so that the induction is smooth. So this condition is nothing but that every f is fixed by some compact open subgroup, which is same as saying that f of G times kf is equal to f of G. Okay, and the action of G on any function is given by right translation. So this is a smooth induction, and then there is a variant of this which is called as compact induction. So this is going to be a sub-representation of smooth induction consisting of only those functions which are compactly supported modulo H. It means that if you look at the support of F and its image in G mod H, right? I mean under the quotient map, then the image is compact for the quotient topology in G mod H. Okay. Maybe, yeah. Note that if H is a subgroup such that G mod H itself is compact, then this sub representation is actually the whole smooth induction. So we can see the examples of representations that we saw last time in this language. For example, if you remember the space of compactly supported smooth functions on G, this is nothing but the compact induction of a trivial representation from a trivial subgroup to G. Okay, and then if you take some compact open in G and consider a sub representation of this consisting of all functions which are left K invariant, and it is nothing but the compact induction from K to G of a trivial representation. And maybe maybe yeah. So we also introduced the convolution product last time on this, and these were elements which are indicator functions on the compact opens, and this star is a convolution product. So you can easily see that this space here is nothing but the ek star. Uh, yeah, this whole Hicks algebra. And if I mm, multiply by ek on both sides, I would get the subspace of k invariants of this representation, which is nothing but I mean the subspace of uh, k fixed vectors of the compactly induced representation, which I can express as k equivalent homomorphisms from trivial representation to this compactly induced representation. And by Frobenius reciprocity, this is nothing but the endomorphism ring of this representation. So the point here is that this algebra, when you multiply by these indicator functions on both sides, you get a sub algebra which is isomorphic to this endomorphism algebra. And now this sub algebra has a unit element, which was not true for this whole Hicks algebra. The unit element here is nothing but the what is the unit element here? It's the identity map here. Okay. Let's yeah, so these are two standard ways of constructing smooth representations of G from those of subgroups. Let's look at the properties of this functor. So compact induction, I briefly mentioned that this equality follows from Frobenius reciprocity, but actually well, okay, I mean yeah, it's actually very much similar to the case of induction in the representations of finite groups. Okay. Anyway, so the properties, yeah.
So if I take endomorphisms of the entire induced G representation, not the compact one, is that too big? Is it like this compact induction is the sub of the original induction, right?
That yes.
Smooth induction.
Yes.
And if I take
Yeah,
the
yeah,
end the endomorphism G endomorphisms of that is like that cannot be represented like this.
Oh, so
I guess the map
thing
from
is,
if I take an endomorphism of say induced representation, does it restrict to endomorphisms of the compact representation? Probably
no.
It may not preserve, I guess. Okay, I guess.
Yeah, that's what I was coming to. The Frobenius reciprocity for the whole smooth induction uh, is different from here, because the here we are inducing from compact open. It is also important that it's a compact open subgroup. So basically, when I say that the image image in this quotient is compact, it actually means that the image is supported on finitely many cosets, because H is open. So G mod K is has a discrete topology. So that's why this this is the compact induction. When you are inducing from a compact open subgroup, it behaves very much similar to the induction in the representations of finite group situation. Okay, yeah, let me.
Okay, thanks. Yeah.
Okay. So yeah, but okay, let me move on and let me think, because maybe I will answer what is this endomorphism algebra of the full induction, right? Maybe at the end of talk. Is that okay?
Yeah, sure. Go
Yeah.
ahead. Please. Yeah, sorry.
So I briefly mentioned some properties of smooth induction. Um, so it's an exact functor. It preserves short exact sequences. The Frobenius reciprocity for smooth induction uh, is different from the compact induction here. It's a left adjoint of the restriction functor, which here the compact induction was the right adjoint. If you see, um, it is both left and right adjoint compact induction, but in general, smooth induction is only going to be left adjoint. Um, Now, from now on, I'm going to consider my p-adic group to be a group of rational points of some connected reductive group defined over some p-adic field F. And my closed subgroup, let's consider it to be a group of rational points of F parabolic subgroup of G. then this smooth induction from H to G is also called as parabolic induction. And in this situation, this parabolic induction also preserves admissibility. So meaning if W is admissible, then the induction of W is again admissible. And the reason is easy to maybe intuitively understand, because admissibility is nothing but some sort of finiteness property. And when P is a parabolic of G, we know that the quotient is compact. So maybe you are not inducing um, to a very big sort of you are not inducing from a very small subgroup to a big thing in some sense. Uh, in the last talk, I gave an example of a compactly induced representation which was not admissible, and I mean it's for example this representation here. This is not admissible because again, if you consider the if you consider the space of k fixed vectors of this is nothing but where this is nothing but the functions from G to complex valued functions on G which are by k invariant. And last time we said that if you decompose G into k double cosets, then the decomposition is into countably many k double cosets. So the dimension of this space is not finite. Okay, and the point here was that G mod k is not compact. G mod k is in fact, it's far from being something like compact. But when you are inducing from parabolic subgroup, G mod p is compact, so it preserves admissibility if W is admissible. Okay, so when we are in the situation from inducing from a parabolic subgroup, there are interesting examples of representations. So let's consider the simplest sort of non-trivial p-adic group, that is GL to QP, and let P be the subgroup of upper triangular matrices, which is a semi-direct product of diagonal matrices and upper triangular unipotent matrices, T semi-direct with N, and let W be a trivial representation of of P. Then what is this induction of W from P to G? This is nothing but all smooth locally constant functions. I should have written compactly separated, but it doesn't matter because the space itself is compact. So all locally constant functions on G mod P, but G mod P is nothing but this projective line over QP. Okay, so you can think of this as some object coming from geometry, that all locally constant functions on projective line over QP, they, yeah, it's obviously a representation of GL to QP, and it is not irreducible because clearly it contains constant functions. But so if I take the quotient of this representation by this trivial representation, that is this representation on the space of constant functions, then the quotient is irreducible, and this is what is known as the Steinberg representation of GL to QP. In general, uh, yeah. In general, how do representations of G which are induced from Borel look like? Well, they come from inflation of characters. So, uh, so see that the P is a semi-direct product of diagonal times unipotent part of P. So diagonal, you start with some character, smooth character of QP star cross QP star, and then inflate it to P. That means you let N act trivially, and so uh, uh, lift the action from T to P by letting the N act trivially, and then you induce from P to G of this representation. Now this is irreducible if and only if chi1 and chi2 satisfies some condition. So in the first example, chi1 was equal to chi2 which was equal to trivial character, so it wasn't irreducible. But generically, this is always irreducible, and these are called principal series representations of GL to QP again. And in general, well, I don't want to maybe go into discussing what are Steinberg and principal series for general p-adic reductive groups, but just to give you some idea, these are sort of important types of representations. Okay, so let's right. So I want to now uh, talk about a functor which goes in the other direction from G to P. So clearly there is a restriction functor, but that is sort of uninteresting. When my subgroup is a parabolic subgroup, we have another very important functor which is called Jacquet restrictions or Jacquet functor, and that's what I'm going to now talk about. So let P be a parabolic subgroup of G. So again, I mean here G is going to be the group of rational points of a connected reductive group. And when I mean parabolic subgroup of G, it means that it's going to be a group of rational points of a parabolic algebraic group of G. And then this is the Levy decomposition. Again, both these are going to be some group of rational points of the corresponding algebraic groups defined over F. So let P be a parabolic subgroup of G, and now let's start with a representation of the bigger group G, pi comma V, and let's consider the space of n co-invariants. N is the unipotent radical of V. Okay, so what is this V sub n? It is nothing but V quotient out by span of all vectors of the form of nv minus V, where nv is the action of n on V. Okay, so this is the largest quotient of V on which n acts trivially, and since P normalizes n, this is also a representation of P on which n acts trivially, so this is going to be a representation of M. Okay, so this V sub n is a representation of M. So starting with something connected reductive, starting with a representation of a connected reductive group G, we obtained this V sub n, which is a smooth representation of a, again some reductive subgroup of G. Okay, M is the Levy part of P. Okay, so this is called as this construction is, I mean, as a construction, it's very easy to understand, and it is called as the Jacquet module of V with respect to P. But this has very important consequences and very non-trivial properties. So, okay, so what are the properties of now this functor which goes from representations of G to representations of M? So, again, this is going to be right adjoint of smooth parabolic induction. So this is sort of easy to check from this Frobenius reciprocity. First, you restrict to. Okay, so let's take a look at this thing. So what does this mean? So if I have a representation W of M, then I inflate it to P by letting N act trivially, and then induce it to G. So this is how I get induction of W. And when I have a representation of G, I look at its N coinvariance, which is a M representation. So this actually this bijection actually follows from this here. So right. So this is the yeah, this is the sort of restriction we are interested in from G to smaller subgroups. Again, as similar to parabolic induction, this is exact, and maybe a quick sort of just maybe sort of argument here is the following, that N, so this unipotent radical or N is an nilpotent subgroup, so it's a it is the union of its compact open subgroups. And then using that, one shows that the kernel of the quotient map from V to its coinvariants denoted by V N, this can be written as all vectors on which the action of some compact open in N vanishes. So, like, I mean, if you recall this, yeah, let me maybe go back to the first talk. Yeah. So we for each compact open, we I said that the action of this indicator function of compact open on V is actually a projection map onto k fixed vectors of V. So here, okay, now and this sorry, and this action of pi ek was defined. Yeah, was defined here. Pi f of V is this. So here, a similar sort of reasoning gives us that the kernel of the kernel of the map from V to its quotient can be described as so you can think of this as a replacement of V upper K, and the the kernel was exactly pi of ek of V equal to 0, and pi of ek was defined similar to this integral. Instead of now compact open in G, here we are considering compact open in N. And okay, and then once you have this description of V mod Vn, then the exactness is sort of straightforward to prove. But anyway, and third important property is that it also preserves admissibility. When you start with some admissible representation of G, the Jacquet module V sub n is again admissible representation of M. I am not going to prove these things. Maybe just one example. How does this Jacquet module look like? It's so let G be GL to QP and P be the upper triangular matrices. Then the recall the Steinberg representation and the Jacquet module with respect to the upper triangular unipotent matrices. Its semi-simplification is nothing but sum of two characters. So where this is a trivial character, and this is the modulus character of P, which is explicitly it is given by upper triangular ABD mapping to AD, the p-adic norm of AD inverse. Okay, so there is I wanted to just state this that this another very important property of parabolic inductions that they are also left adjoint of it's also left it is also left adjoint functor of this Jacquet module, but here the sort of the it looks a bit different because here we are inducing from opposite parabolic. So this is P bar, and one has to twist on the other side, one has to twist the M representation by this modulus character. So I mean, let me go to, yeah, so this is the right adjointness of the parabolic induction, which is it's right adjoint to this Jacquet modular functor, but yeah, if it is also left adjoint to Jacquet modular functor, but then you have to, if you are considering here the usual P, then you have to take here the Jacquet module with respect to opposite nilpotent, and that's the thing. This is called the second adjoint. It's again a very non-trivial fact, non-trivial property of the parabolic induction, and it's just I just wanted to mention this. Okay, so let me now, after having seen some examples of induced representations, let's come to important class of representations, which are supercuspidal representations. So let pi comma v be a smooth representation of G. Then pi comma v is called supercuspidal if for any vector v and any linear functional in its smooth dual, the function complex valued function on G, which is given by small g, is mapping to v tilde evaluated on G action of G on V. This function is compactly supported modulo the center of G. So this kind of, these are called as matrix coefficients, these functions. So this is a matrix coefficient corresponding to this pair V and V tilde. Because when V is actually a finite dimensional vector space, this is exactly a entry in the matrix corresponding matrix. Okay, so this is a definition of a supercuspidal representations, but there is a very important character equivalent definition of supercuspidals in terms of Jacquet modules. Are there any questions so far? Okay, so again here modulo center, compactly supported modulo center of G means that if you take the support of this function, so again let me recall that support means all the points where the function does not vanish, and you take the closure of such a set. Then the support of function you look at the support, the image of support in G mod ZG, and it should be compact image in the quotient. Okay, so there is a right. So I can. It's easy to see that we can. Well, suppose if I take some. So we know that these are smooth representations. So and I want this matrix coefficient to be compactly supported modulo center for every matrix coefficient. So I can reformulate this condition by saying that uh, the function which maps small g to action of ek on g dot v is compactly supported modulo center of g for any vector v and compact open k in g. Instead of giving a definition in terms of v and v tilde, one can easily say give a definition in terms of v and compact opens in g. And this is this sort of definitions will be useful to prove non-trivial properties of supercuspidal representations. So one important characterization which is attributed to Harishchandra is the following. So smooth representation is supercuspidal if and only if the Jacquet module is 0 for all proper parabolic subgroups P of G. So V sub n is 0 for all proper parabolic P with equal to Mn of G. Right. So the okay. So So maybe for when G is the general linear group, let me maybe go through some steps of the proof. So there are two important reductions that one shows that pi is supercuspidal if and only if its restriction to a subgroup G upper 0 is supercuspidal, meaning that so this is a subgroup of all matrices whose determinant is a p-adic unit. So instead of checking that this function is compactly supported on whole of G, one only checks it on this subgroup, and this equivalent condition that Vn is 0 for all proper parabolic. This is again equivalent to saying that it is it vanishes, the Jacquet module vanishes for all proper maximal standard parabolic subgroup, because again this construction of Jacquet module is transitive. So if you have some unipotent radical sitting inside a bigger one, then one can always reduce to something called maximal parabolic subgroups. And so these once you have these reductions, one uses the Cartan decomposition for this subgroup here, and again the description I mentioned for this kernel from V to Vn, that is Vn here, this description. Using these two descriptions, one can show this for GLNF. And I suppose the similar argument can be should be worked for any reductive proof. Okay, right. So there are many important consequences of this theorem. The first, I am writing these consequences as some sort of slogan. So the first corollary is that supercuspidal representations are building blocks of all irreducible representations. So this is so what does this mean? So this means that if I give you any smooth irreducible representation, it always occurs as a sub representation of a parabolic induction of a supercuspidal representation. So if you understand supercuspidal representations, then by parabolically inducing them, you know all smooth irreducible representations. I mean, okay, you need to understand the. So the thing is, to understand all smooth irreducible representations of G, you need to understand supercuspidal representations and the irreducible subquotients of parabolic inductions. This is the uh, upshot of this corollary. And next slogan is that supercuspidal representations are something truly native to the group G. So this means that, again, these parabolically inducing representations, they actually come from representations of smaller subgroups, but supercuspidal representations are actually, they are the representations which do not occur, which do not come from smaller subgroups. And this actually comes from just the Frobenius reciprocity, because okay, where was that? Yeah, so if you just stare at this equality here, so if V is a irreducible supercuspidal representation, then the Harishchandra's theorem says that this is 0. So this means that there are no maps, G maps from V to any parabolic induction. So this means that V does not occur in the parabolic induction. Okay. Yeah, again, so this corollary mathematically means that any reducible supercuspidal representations is not a sub-representation of a parabolically induced representations for any proper parabolic subgroup of G. Actually, the correct way of calling such representations as just cuspidal, not supercuspidal, and supercuspidal will be something like that, a sub-representations which is not a subquotient of a parabolically induced representation for any proper parabolic subgroup. So supercuspidal should, I think I should call these as just cuspidal representations. But again, for groups of our interest, these two notions coincide. So it's okay. So third consequence of this theorem is that right, why the name supercuspidal or cuspidal? Yeah, so the thing is, if I have a supercuspidal representations, then every matrix coefficient, right? So which I'm denoting by F sub V comma V tilde is a cusp form on G, meaning that the integration over the unipotent radical of any proper parabolic vanishes. And so here the proof is just one line, so I decided to include it. So just unwind the definitions here. So if V is a supercuspidal representation, then we know that V is equal to Vn, right? Because its Jacquet module is 0 using Harishchandra's theorem. So that means V is equal to this Vn. So it means that any vector is a finite linear sum of vectors of this form. So I'm looking at a particular vector like this, and then you can check that this integration of this function vanishes by just some sort of change of variables from small n mapping to n in n0. So this is why they are called cuspidal representations, because every matrix coefficient is a cusp form. And maybe going back to the beginning of these lectures, one can also try to see how this definition of a cusp form is related to the cusp forms that one sees in the theory of modular forms. So where was that? Yeah, so if you right, so if you have some F cusp form, Then the corresponding automorphic form is a function on adelic points of G of F, and that function is again a cusp form, uh, in the sense that if you integrate it over unipotent radicals of proper parabolics of G, then it vanishes. Okay, so this notion of a cusp form. Okay, where is that? Yeah. So this is just the local notion of cusp form coming from the global theory. Another important consequence of this theorem was that one can show that any reducible supercuspidal representation is admissible, and since
So for
supercuspidals are
supercuspidal,
built.
the cusp form comes as a metric coefficient. What about cuspidal representation, which are
Sorry, what?
you're saying that for supercuspidal, the matrix coefficients are the cusp form.
No. I said right. I should call this cuspidal representation, not supercuspidal.
It is a
Huh?
typo.
No. The thing. So these two notions coincide for many
Okay.
groups, supercuspidal and cuspidal.
And when they don't
Uh,
coincide,
huh?
when they do not coincide for some groups.
Yeah. So then then supercuspidal and cuspidal are different. Yeah. But then this corollary is true for, well, anyway, supercuspidal is always cuspidal. So this corollary is anyway true that its matrix coefficient is cusp form. So that's okay. Cuspidal need not be supercuspidal. Cuspidal means that the representation does not occur as a sub-representation of a parabolic induction. Supercuspidal means that it does not occur as a sub-quotient of a parabolic induction. So supercuspidal is a stronger motion. Is that what you were asking?
Yeah.
This is anyway true. This corollary is true. Yeah. So I was saying that another consequence of that theorem, the characterization of supercuspidal in terms of Jacquet modules, one can show that any irreducible supercuspidals are admissible representations. So they some sort of finiteness. They have, in some sense, they satisfy some finiteness condition, and then that would imply that any smooth irreducible representation is admissible, because any smooth irreducible is a sub representation of a parabolic induction of supercuspidal, and parabolic induction preserves admissibility. Okay, so then what are examples of supercuspidal representation? Unfortunately, this is again the difficult part of this theory, and it is understandable that these representations do not come from a smaller subgroups. So construction is not so easy, and classification of supercuspidal representations is a sort of the main research theme of representation theory of p-adic groups, constructing all supercuspidal representations. So let me give you some idea how one can obtain some how one can construct supercuspidal representation. So let's now look at subgroups which are open compact modulo center subgroups. So something like you take GL2ZP in GL2QP and take the center. So the product of the center and GL2ZP. So this is an open compact modulo center subgroup. And now consider the smooth representation of this subgroup. Take a compactly induced representation from such a subgroup of this W. Now, if you are given a matrix coefficient of W or sigma, then one can define a matrix coefficient of, one can actually define a function which becomes matrix coefficient of for this compactly induced representation. This is this fact. So if I start with f as a matrix coefficient of sigma, and I define a function g, which is nothing but when restricted to h, it is f, but and 0 otherwise, then it is actually a matrix coefficient of pi. So this means that but then now what is this matrix coefficient? This is a matrix coefficient which is compactly supported modulo center, right? So right. So this fact implies that if I start with some non-zero matrix coefficient of sub-representation, I get a non-zero matrix coefficient of pi, which is compactly supported modulo the center. And existence of one such non-zero matrix coefficient guarantees that every matrix coefficient is compactly supported modulo the center if pi is irreducible. So if okay. So how do we construct supercuspidal representations? I start with some compact, some open compact modulo center subgroup and some smooth representation of that subgroup, and then compactly induce it. If this is irreducible, then that representation is going to be supercuspidal. Okay. So let's maybe explicit example. Let me give you. So I'm now here taking h to be GL2 Z2 p-adic integers. So this is of course open compact modulo center subgroup because this itself is compact open. And look at the character of this subgroup, which is given by which is actually coming from the sign character on the symmetric group of 3 elements, which is isomorphic to GL2 F2, and then you pull it back to GL2 Z2. And then just induce this character from GL2 Z2 compactly is important, to GL2 Q2, and then one shows that this pi is irreducible, so it is supercuspidal. Okay, so I mean, I haven't justified many things here, but actually constructing such representations is not very easy. This is some very easy and explicit example, but otherwise constructing compactly induced representations from open compact modulo center subgroup which are irreducible is not easy, and that's why the supercuspidal representations are not very easy to construct. And there is a in fact conjecture which is true for GLN, that all supercuspidal representations of GLN, they occur, they are actually of this form for some open compact modulo center subgroup. Yeah, I think that's all I wanted to say. So some references I want to mention. These two are classical references to start with the representation theory of p-adic groups. I followed this third reference, and I would highly recommend the fourth reference, which is a very nicely written notes of which are available on the web page of this mathematician. Okay, so are there any questions, or let me now go back to this question here, if there are no other questions.
Yeah,
Let
you
us
discuss
thank
this.
Mihir. Yeah, are there any questions?
Okay, right. So yeah. So first of all, okay. In order to have some Yeah, let me just think for 2 minutes. Yeah, the thing, right. The you can, of course, consider this endomorphism algebra of smooth induction from K to G of trivial representations, but that is that probably is not very useful. Yeah, it's going to be very probably huge algebra, and the thing is why we introduced this space here, because we in the first lecture we saw that smooth representations are same as modules over this algebra. So this was enough to consider this compactly induced representation instead of considering the whole
So
smooth.
it's a alternative characterization, is it? Smooth representations are modules over such.
Yeah.
I
Smooth
see.
representations are modules over this.
Yes.
Yeah, that.
So this EK is supposed to be some sort of characteristic function on.
Yeah, on which is supported only on K.
I say.
Compact open. Yeah.
And this star is some sort of this usual this what is it involution? No, what is it?
Yeah, convolution.
Convolution.
Right. Yeah.
Okay. Thanks. Any more questions? Okay, I guess then we should end the session.
Yeah.
Okay, thanks, Mihir again.
Yeah, you're welcome. Thanks.
Thank you, Rakesh, to you also to make this. You can thank.